Let's get started with our algorithm of dynamic programming. Here we have a new document made on Replit, and the most important thing is to always divide the program in three different sections. So these sections are referred to as the modules, the data definitions, and finally the actual code where the implementation of the algorithm actually takes place. And this is very similar on how we bake cakes, right? Baking cakes is very similar to programming in the sense that we need to follow an algorithm, a series of instructions that, if followed properly, are going to always guarantee us the same result. So we divide the program in data definitions to understand what information enters the program, which also comes with a clear understanding on how the algorithm works. In this particular case, we are not going to be using modules, so we can just refer to these two sections. Let's focus on the data definitions. These are the information that has already been discussed in the tutorial, so I'm just going to simply move ahead and paste that information here. Notice that the information that this particular data represents is different to its data type. It is important to declare both, and you're going to find it here in these comments. So the first type of information that we need to add for the algorithm of dynamic programming is going to be the penalizing costs. A penalizing cost represents what penalty we should give to a particular transformation or pairing between two different nucleotides. Transitions are those that include changes from A to G and vice versa, or C to T or vice versa. Transversions, however, imply a change in molecule, purines or pyrimidines, which means that they are less frequent, and therefore in the hypothesis of how our model works, they should have a higher penalty. They're just harder to find. And that's why we're going to add them a penalty of 3. Remember that the algorithm goes by starting at 0 and then subtracting from 0, getting more and more negative scores. So the value of those scores are going to be given by the magnitude of these penalties. The match happens when we have the alignment of two nucleotides that are exactly the same. And finally, we have the penalty involved in the insertions of gaps. Then we have the sequences, which are going to be in this case only 2. We can add more sequences, and programs that deal with multiple sequencing use several types of tricks like multiple or nested pairwise comparison in order to achieve the alignments. But let's keep things simple in this case, and let's just keep a two-dimensional matrix by comparing sequence 0 with sequence 1. Then we have the actual matrix of scores. This matrix represents a matrix made out of zeros that you have already seen in the previous YouTube tutorial. So let's jump straight into the code. What do we do? Well, the first thing that we need to do is to traverse the matrix. And the best way to traverse a two-dimensional arrangement is given by this template. This template is easy to derive. It normally happens when you have a list or an iterable object, and the best way to go through every single item inside of them is through a for loop. That's actually what for loops were originally designed for. So in this case, we're going to simply copy this template, which is a two-dimensional for loop, and we're going to paste it here, making sure that we get rid of the comments. So look at these 3 dots here. So in the same way that the English language contains subjects and predicates, here these 3 dots will represent the predicate, which should not be confused with the technical term in computer science of what a predicate is. It's simply referring to the verb, in other words, the action or function that is going to be affecting or receiving this element called PT. So what do we need to do? Here is saying that we need to do something to the element called PT. And that is going to be evaluating the penalty of inserting a gap to the right, inserting a gap to the bottom, or adding or evaluating the diagonals. We will start by adding a new local variable called the score. And the score is going to start with a null value. There is not going to have anything there in order to address any issues that could happen down the road with the pipeline, so that we can deal with them during the execution of the algorithm, during the evaluation stage. Then we're going to make sure that we have access to the y-axis and the x-axis given by the rows and the particular cells inside of these two-dimensional matrix respectively. We are gonna add a y and an x here in the for loops. Now, this represents two elements that have to get unpacked, and the only way to do that is by adding a new method called enumerate. So we're gonna enumerate the matrix, and we're gonna enumerate the row. Now that we have the elements in the coordinates x and y for the row, for the particular row and the particular column, we need to evaluate three cases. The first one happens, let me get my pen here. So the first one happens when we are in the very first column and the very first row. So we are here. That means that there is nothing on the left so that we can move right, and there is nothing below, and there is nothing above so that we can move down. So in this case, the score is going to be simply 0. The second case is when we are in the first row, in which case we can only go right. And the third case is when we are in the first column, in which case we can only go down. The last case, which is going to be an else statement, is going to be that one that allows us to work anywhere here in this subdomain of the two-dimensional matrix that contains elements to the left and elements above. And through the magic of video editing, we have here the different if and else statements. So in this particular case, x and y are both 0, so we determine that the score is going to be set to 0. In the second case, when the value in y is equal to 0, we can only move to the left. We can only move to the right coming from the left, which means that we are going to need to evaluate the previous score to a new score that occurs when we add a gap. And in this case, the score is going to be equal to the call of a function that we don't have yet, but we know we're going to need. Sometimes we call this wishing for a function. And the name of the function is going to be called evaluate. Evaluate is going to receive two things: the position in x, the position in y, and a particular direction where it's coming from. In this case, I'm just going to add L, letting it know that we're coming from the left and we're supposed to move to the right. As you can probably guess, going down instead of right is going to require the same idea, however, coming from the top. The else statement here is where the most interesting part of the algorithm happens. So basically, we have three possible options coming from left, from top, and from diagonal. We have the three possible cases that we need to evaluate. And then we need to keep the score that is the biggest or the closest to 0 among the three of those. So it seems we need to evaluate the three cases. To do that, however, I'm going to start by adding a local variable that is going to contain the local scores. We're simply going to call this scores. Then we call the function called evaluate for the left, top, and diagonal. And finally, we retrieve as the score the maximum element inside of this list scores. Notice that the score is being extracted from the list scores, and notice that each of the three different cases are being evaluated and they are being appended in a particular order. First from horizontal, left to right, then vertical, top to down, and then diagonal. That means that this horizontal evaluation takes the index 0. The vertical evaluation takes the index 1, and the diagonal is always going to take the index 2. The last thing we do is to make the value of the matrix at the coordinate x and y, first the rows, then the columns, equal to the value of the score that we extracted. So let's work with that evaluate function. So what does evaluate do? So evaluate is going to receive a position in x, a position in y, and a string that represents the direction where we are assigning the particular score. And here we have the following cases: if it is coming from the left, if it is coming from the top, or if it is coming from diagonal, which is a free value given by elimination of the other two cases, so we don't need to have a particular string that says D for diagonal. If it is not left or top, it has to be diagonal. So what do we do if the element is coming from the left? If the element is coming from the left, it means that there is an index in the x-axis -1 that contains the value of the score in this particular row called y, in this particular column x -1, and we need to subtract the particular value of adding a gap. That means that we need to return the position of the score at the matrix in the index y and x -1, and let's subtract from it the value of the penalizing score when adding a gap, which in our case is penalizing cost of, and because it is a dictionary, we add the square brackets and we select the key called gap. As you can imagine, the same happens in this case, however, for the vertical direction. And here I invite you to think about what changes have to happen to the identity of the cell in this matrix. If going from left to right affects x, well, it seems that going from top to down must affect y. And if we're coming from the top, it means that we are going down. We need to evaluate the previous row at the index y -1. And then we also subtract the penalizing cost of our gap. What happens with the diagonals? So here's where things get a little interesting. So if the index in the y-axis of the sequence 0 is the same as the element in the index x for the sequence 1, it means that this is a perfect match. G goes to G, A goes to A, etc. In that case, we don't penalize. We just return the current score that we have in the previous coordinate x -1 and y -1 because we come from a diagonal. So we ask if the sequence 0 at index y is equal to the sequence 1 at index x. And if the answer is yes, we simply return the matrix at the index y -1, x -1, diagonal top left, and then we subtract the penalizing cost of the match. Now we know that this value is 0, but we make a reference to the key of this dictionary penalizing costs anyways, because it would be easier to change it later. This way I can just change this 0 to something else if I want to penalize even matches, or change it to negative values so that the process is that of addition down here. Is that the only case scenario? Well, not quite. Here, we need to evaluate in the case that the sequence 0 at index y and the sequence 1 at index x are not the same letter. And in that case, we need to evaluate if this is a transversion or a transition. We know it's not an insertion of a gap, and we know it is not a perfect match. So we need another helper function that is gonna return that information right away. This is gonna look a lot like the previous return that we have here, except that instead of adding the penalizing cost of a match, we are just gonna call that helper function that is gonna be called evaluate transitions transversions. And it is gonna receive the sequence 0 at index y and the sequence 1 at index x. That is evaluate. So let's just work real quick through the other helper function. Evaluate transitions and transversions. We're gonna get the sequence 1, the sequence 2 as parameters. And what we do is first to define somewhere, could be here, the different combinations of transitions and those that are transversions. We're gonna start with NM, which is the nucleotide matrix of transitions and transversions. This is going to be a two-dimensional list that is going to contain as its first element the combination of A and G, then the combination of C and T. Once we have them, we are going to evaluate if the nucleotide in the sequence 1 and the nucleotide in the sequence 2 are both inside of this first element of the list. If that's the case, then this is a transition. If S1 is A or G, and S2 is A or G, then we assign the penalty of a transition. The same applies to the second element in the list. If S1 is C or T, and if S2 is C or T, then it's also a transition. Anything else has to be a transversion. So how do we do this? Well, we are simply gonna evaluate each of the nucleotide types in the list NM, which is a series of sublists. And we're gonna ask if S1 is in NT and if S2 is also in NT. If the answer is yes, it means they are both in the same type of molecule, and therefore we return the penalizing cost of a transition. So if we finish going through the if statements and we haven't returned, it means that this has to be a transversion. So we're just simply going to return the penalizing cost of a transversion. And we are done with the second part of these helper functions. Okay, so at this point, let's make a quick pause and let's just take a look at what the matrix is looking like right now. So if we look at the value instead, if we look at the value printed in the console, we're gonna see that the first row seems to indeed match the values, the accumulated values of gaps 0, -2, -4, and -6 that we saw in the explanation of the algorithm during the introduction to this problem. So it seems that we are doing great. The next thing we need to do is to invert the position of this matrix in order to traverse it. Now that we have the scores filled up, we are going to need to go the opposite direction. The first thing we're going to do for this step 2 is to add a series of local variables. These ones are going to be referred to as follows. For sequence 0, we're going to have an aligned string that is going to be the final version of the sequence 0. The same thing, but for the sequence 1, the aligned version of it. And then we're going to have a string that starts as an inverse version of the original sequence 0. This syntax that looks very, very weird right here is the way that we have to invert the direction of a string. So we're simply flipping it over. The same happens for the sequence 1. And finally, we have a reverse matrix. If you are not familiar with this context right here, with this particular syntax, this is called list comprehension. And we have a two-dimensional list comprehension. So here we have the inverse version of each of the rows, which is going to flip the row horizontally. And we're going to do that for every single row in an inverse version of this matrix. That means that the last elements are going to be inverted and now are going to be the first elements in the array. As I mentioned before, we are doing something very similar to put a mirror in front of this matrix so that it gets flipped horizontally and also vertically. The reason why we do this will become quite evident in just a second. We are going to start by creating a new variable x and y. Now, this is a formal traversing that is not going to be done with for loops, because the intention is not to visit every single tile or every single element inside of the reverse version of the matrix. The purpose is to carefully navigate the path that we already created while adding the last versions of the alignment as underscores for the gaps or the identity of the nucleotides, depending on which path we are choosing. In this case, we're going to use a while loop. A while loop that is going to evaluate if the number of the rows is still within the boundaries of the reverse matrix, component, which represents the rows, and whether or not x is still within boundaries of the reverse matrix at the index, which allows us to extract the length of one particular row. Now remember that this is a matrix where every single row contains the same number of columns, but I prefer to have it this way. Another chance is to change this from y to 0 because the length will not change. And if the answer to these two questions is yes, then we're going to evaluate the following cases. If this is the last row and the last column, we're simply going to keep the letters, right? So if this is the last element in Y and the last element in X that is still within the boundaries of the matrix dimensions, then we are simply going to respect that whatever combination of letters we have there. And here we're going to add to the sequence 0 the respective version of the reverse sequence at the index Y and X respectively. Remember, Y is for sequence 0, what X is for sequence 1. The sequence 0 aligned is a string version that we are populating, we are filling up, and the element reverse sequence 0, remember, has to be reversed because we are going backwards. Because the algorithm at this point is building from the back to the front. Lastly, we're going to simply add 1 to X and 1 to Y, which will allow us to exit the while loop. The second option is that we have found the last row, in which case we can only go right by inserting gaps. So the sequence 0 will get added to it an underscore, while the sequence 1 will get added to it the nucleotide that belongs at the index X in the reverse sequence 1. And finally, we move to the right in this matrix by adding 1 to X. As usual, you can imagine that the inverse thing happened in the next evaluation of the case when the problem is with the columns and we are in the last column, in which case we can only keep going down. And here it is. Now, what happens in the most interesting case, which is where we are, in the midst of the fight, we are right in between, we are right in the middle of the matrix. We are making our way through the decisions. What happens in that case? Well, just like we did before, we need to evaluate going right, going down, or going diagonal. This time picking the scores that are the closest to 0 in every single one of these 3 different options. We will start by adding these local variables. The variable called minimum scores is a list. Something that we have already done. We added an iterable object that is going to get appended to it 3 different components. One coming from the right, one coming from below, and one coming in diagonal. Once we append these elements, we're simply going to pick the index. In this particular case, the position in this arrangement called minimum scores, where the maximum score has been found. So I guess I should call this not minimum but maximum scores. And with that we extract one position 0, 1, or 2 if it comes from right, down, or diagonal. Now that we know which index we picked, we can evaluate 3 different cases through if statements. In the first case, we are coming from the right. So what we do is to add an insertion to the sequence 0, while adding the nucleotide at the index X of the sequence 1. And then we move to the right. Notice that this part is identical to the one that we already went through, to one of the cases that we already went through, that is this one right here. And the rest, as they say, is history. The second part is going to be the inverse version of it, which means that we're going to add to the y-axis and we're going to add the underscore, the gap, to the sequence 1 while keeping the nucleotide in the sequence 0, the reverse version of it, in the index y, and adding it to the aligned sequence 0. The last case here is that in which we are going to respect both nucleotides. One for the sequence 0, one for the sequence 1, because we come from the diagonal, and then we add both to X and the Y-axis. But these sequences are inverted. Finally, to finish this algorithm, we just need to flip them back. We generate 2 more local variables. We recycle the names sequence 0 and sequence 1 aligned by using that old trick of the 2 colons with the -1 for the sequence 0 and the sequence 1, and we can finally just print the sequences. If we run this code, the program should be done. and we got our sequence alignment. So let's just copy this real quick and let's put it in a text editor so that we can see it a little better. Here we are, and here we have our sequence alignment. Now, at the beginning, you can see that the algorithm may have seemed like it was having some troubles when trying to align the beginning of the sequence, but when the information starts overlapping a little better, you can see that the sequences perfectly overlap. That is the power of this algorithm called dynamic programming. And this right here represents the best hypothesis we have on how these two sequences overlap each other. Now, some natural questions that may arise is, what happens when I modify the parameters slightly? That's something that you should definitely try. What happens if I give more weight to the transversions than to the transitions? Not from 3 to 1, but from maybe 10 to 1. What if I heavily penalize gaps? These are things that are going to greatly modify your results. So it's important that you play with this algorithm.